demonstration, so I try to get slowly through the material. We've done this. We've defined the serial execution time as the best execution time you can have on a sequential computer. Parallel execution time on a P-processing machine. We defined the overhead function. Let me put it on the board here also. After wiping out some math. So the overhead function is the number of processors times the parallel execution time minus the sequential time. And the speed up, which is TP divided by TS divided by TP. And I explained to you the difference between the parallel execution time with P is 1, right, being the parameterized version of the parallel code versus the original sequential code. And I gave you the examples. Then I've shown you the complexity of adding n numbers on n processors. And we did that by taking an example of 8 processors, each having a number equal to the identity of the processor, and then in a binary tree, we reduced the final sum, with the assumption that each step takes a constant amount of time, one addition and one communication step, right? Just for the analysis. So that's realistic is a different thing, but for the analysis is this, and then we achieved that the parallel execution time is log n, because we have log n steps, right, which you can easily see, and that therefore the sequential execution time is n over log n, because we have n minus 1 additions to do for n numbers, which is still order n. So it's n divided by log n. Okay, that's what we done last week. Now I want to introduce the WT representation. WT is used heavily in the second half from the book of Yaya, and I guess Witteveen will use it to lead you through the algorithmic stuff. So it's good to also have a small introduction and use of this WT representation. It stands for work time representation. It's the work time model. The work in this model is equal to the total number of operations used, where n is the size of the input parameter, right? In number in steps. Of course, in the end you can weight it for if a division takes more time than a multiplication, you can do all kind of detailed other analysis, but for this course we don't do that. We assume that each operation costs the same amount of computational time. Now there are two WT representations, work time representations. The upper one of the algorithm uses an unbounded number of processors, right? And the lower work time representation of the algorithm uses the scheduled algorithm on P processors, with P smaller than n. So there's an upper and a lower one, right? Well, premises is that, preliminary is that we organize an algorithm in a series of sequential and parallel steps. So if we have an algorithm, we have a serial step, then we fan out, say, right? We reconvene, we fan out again, and we may fan out here more, right? But here, in the end, we come back again. Something like this, right? It's series parallel. So it's a series of sequential and parallel steps. So the parallelism can be nested, right? That is not a problem. Well, what would be the upper representation of our algorithm for adding n numbers on n processes? Well, this is the algorithm. The input is the number n, if you can read it, it's a bit small here, which are stored in an array. The output is a sum s, where we add all the elements, right? And I give the algorithm in pseudocode here. So first of all, we copy the all the elements A in a structure B. Then we do log n in the outer loop sequential steps of a number of parallel steps in the inner loop, right? And that's equivalent to the graph you've shown. And you see that the amount of parallel work is determined by the range of I which is spanned in this inequality. And here we do the addition, and then finally we copy the sum, right? Now if we write the number of work here, then we see that this first one is equivalent to n steps, right? Because if we would do this sequentially, we have n steps to do here in this part. This is the second step here, and this is the third step. This is one. This is only one, right? And if we summarize this, then we have two n's plus one step, which is order n, right? The parallel execution time is log n plus 2. Why 2? Pardon?
The first one for parallel execution is 1.
One.
And then the other is the last step.
Yeah. So indeed, this is done in parallel. It's done in a single step, and then you have this log n, and then you have this as a single step. So that's the 2, right? Which is again order log n. So we're back to the original what we derived, right? So you can see the relation between the complexity in the graph and the pseudocode here, right? You can write it down from this code. You can directly construct an expression to a performance expression. Now this is very simple, of course, but if you have more complex algorithms, it's going to work the same way. So the only difference with the previous scheme is the extra copy steps start in the end. So something about maximum speed up and superlinear speed up. If we plot the number of processors against the speed up we ideally have that the speed up is linear in p, right? If I have an ideal program, then I would get s is equal to p. Normally, we won't have that. And we will have a sublinear speed up, right? That is, if the number of processors grows, then we see that the overhead increases and that the efficiency drops a little bit. Now, if we would have a curve like that, we would have superlinear speed up. That is, the speed up goes faster if we add more processors. Now, the question is, how can that be? Right? Are there real cases, right?
The memory access time would get slower if you use more processors.
Yeah, that's these kind of effects are usually the case for some form of linear, superlinear speed up, right? It's only usually in a limited range, and it doesn't extend to all the. And I'll give you an example. Suppose we have a system which can do one floating point operation per memory access. Right? We have a cache which has an access time of 10 nanoseconds and a main memory of 100 nanoseconds. Right? Then the access time is the chance that the data is in the cache minus that's not in the cache, right? Simple. So if we would have an 80% hit ratio, so we have a workload W and we have an 80% hit ratio in the cache, then we can simply substitute into 28 nanoseconds, which yields to a speed of this processor of 36 megaflops, right? Just filling in. Now, what we're going to happen if we split the workload to two processors, right? Each processor gets half of the workload, and then because we have more memory, right, it's highly likely that the hit ratio is increased. So say that it's 90%. Then the access time is 19 nanoseconds, and then the speed per processor necessarily increases to 53 megaflops. But we have two processors, so the speed up is approximately 3. Right? Which is superlinear. Because normally the speed up would only be 2. And that comes back to your remark, just by adding the memory, you have this effect, right? It's not because of the processing speed here, it's because of adding the extra memory that increases the Of course, the question is whether it's scalable. Yeah.
What I don't understand is why would your hit rate go up when you add more memory? Why would the cache hit rate go up?
Well, because you have more cache memory.
Oh, you're talking about cache memory?
Yeah. Because you double the cache memory, right?
I thought you were talking about main memory.
No, you're talking about the cache memory. Yeah. So this is the first example where, and you can sometimes see that in curves, right? So you have to be aware that if you observe a superlinear speed up phenomenon, it might be caused by the cache effect in your system. The second example is a search example. Suppose we have a number of data items which are organized as a tree, and the data item we are searching for, and we're searching according to a key, is located here. Right? Now, to find it, we need a search discipline. Suppose that we have a left first left first, depth first search algorithm, then we're going to search for the item deep down in the tree. It's not here. Then we go up again, and then finally we find it. This takes us 4 times TC steps, where the TC stands for the fact that we compare the keys. Now, if we would have a different search discipline, which starts with the right branch, right, first, then we immediately have it in 1 TC, right, which makes the conclusion that we have a speed up of 4. If we do that, right? Now, what's wrong in the reasoning here? Yeah.
You're just changing the algorithm, you're not distributing it.
No. But is this, yeah?
The serial algorithm isn't the best one.
It's not the best one.
I mean, you have to compare it to the best serial algorithm
Yeah.
for speed up comparison.
Yeah.
This is not the worst case for the algorithm on the right.
No, what do we imply then?
This is, you just made an algorithm that's very efficient in solving this instance.
This instance, right. It only works for this instance. It doesn't work on the average. So on the average, there is no superlinear speed up. It's only for some unknown instances that you can observe it, right? So it's a bit of an example where you can observe for a single item, hey, this goes faster than I would expect. But if you have a lot of items, you can't use it, right? Because you can't use, you cannot change for every search the algorithm search because you don't know anything about where to find it, because it's a key-based search. It's not organized. On the average, there is no superlinear speed up. Right. Efficiency. Efficiency is defined as the speed up divided by the number of processors. Therefore, efficiency is always between 0 and 1. Right? So, or 0 and 100% if you want. So what is the efficiency of adding our n numbers to n processors? Well, it's simply substituting the speed up we have derived divided by p, which is equal to n, right? So it's 1 over log n. Just another type of problem, being slightly more complicated as an example. Suppose we have a stencil type of operation on an array of n by 2 by n by 2, n plus 2. And I take it n plus 2 to have nice formulas, right? There's no reason to take n plus 2 instead of n by n. And the operation I have is typically what you see a lot in image processing, right? For every pixel here or cell here, I take the average of the neighboring elements, right? And I can do only do that for the inner part, right? The n by n inner part, because the border rows you have to keep these separate. Okay, it's easy to see that the sequential execution time is 4, there are 4 operations, 1 plus 2 plus 3 plus and a multiplication. So there's 4 operations which take time tc times n squared. Right, if we do that in one. Okay, so that's the sequential execution time. Now what would happen if we split the data by half? Right? Well, first of all, we have a problem, because if we want to compute this one, we do not have this element here. And vice versa, if we want to compute this one, we do not have this element here. So the first thing we have to do is exchange the border elements here, right? So we have to add a shadow column here to these both arrays, and we have to exchange these two ones before we can do the calculations. Right, if we then try to see what the computation means, is that we first have to do a communication step, which is equal of 2 times the startup time n times tw, right, to the metrics we have derived. Then we do the calculation time, which is for one dimension equal to n over 2. So that's equal to 2 times tc times n squared. And if we take these two together, we end up with the parallel execution time. Right? Well, if we fill this in, we can have an expression for the speed up. Right? So in that sense, we can manipulate with these formulas. To see you that we can also do it for a more complicated example. Well, we leave it for what it is and go to the notion of cost. Cost is defined as the product of the parallel execution time times the number of processors. So we also call that the processor time product. We are interested in cost optimality. And cost optimality is defined as follows. A parallel system is said to be cost optimal if the parallel solution has the same as dotted growth as the sequential solution. What does that mean? That means that these two need the same asymptotic growth, right? Meaning that the efficiency, which is equal to the sequential execution time and the processor time product, has a complexity of 1. Order 1, not 1, order. So that's very important to remember, right? The system is only optimal if the efficiency is order 1. Now, we derived for that in the case if we add n numbers on n processors, then the efficiency is 1 over log n. Now, what can we say about this?
It's not cost optimal.
Then it's not cost optimal. Right. It's not order 1. It's order 1 over log n is not order 1. Now the question is, since reduction is an essential operation in parallelism, can we make it more cost effective in the definition sense as we have here? Well, one thing we can do is first trying to enlarge the granularity and try to do it with less processors than n. So assume that we have going to add n numbers on p processors, right? And let us assume that we have a simple model again where each processor not only contains 1 number but 2 numbers, and derive what the computation time is in that case. Well, what we do is we first transfer the first number and then add it. And the second step, we do the second number and we add it. All right? Then we go on in the next phase we do the same, but then with the partial sums again, etc. until we have the final result. Now, if we calculate the complexity here, we see that the total calculation time is now equal to the local calculation time and the global calculation time. And the global is reduced to n over p log p, and this is also n over p. So the total parallel execution time, this term is larger than this one, is in the order of n over p log p. Right? Now the question is this optimal? Well, if we calculate the cost, which is p times the parallel execution time, we see that now the cost is equal to n log p. Meaning that the efficiency is now 1 over log p. Right? We had 1 over log n, and we reduced it to 1 over log p. So it's definitely better, but is it cost optimal? No. It's not order 1. Right? So this doesn't improve. What can we do more than we did? Anyone has an idea? Yeah?
Maybe use the processors you have more often. Utilize them better.
Sorry?
Utilize the processors that you do have better somehow. Because right now this is a logarithmic summation.
Yeah.
Which means that after the number at a certain processor has been sent to another for summation, that processor just becomes idle.
That's true. But how
what
would
to
you
do,
do
I
that?
don't know.
It's unavoidable that at some point processors become idle, right?
Yeah, because of the reduce.
Yeah. Yeah?
I saw that 7 calculated the addition and then passed it to 6.
Yeah.
If you did 6 to the addition and pass it to 7
Yeah.
also.
Yeah.
And then we have 2 additions in one
Yeah.
step.
You want to improve on that?
Well, if you go back to the last slide, you see that it only in
Which one? This one?
only in 6. There's 6 plus 7, but couldn't you put the 14 into 7 again?
Yeah. And this one? Yeah.
No, the other way, like.
What do you want to do?
So you end up only with 6 plus 7 is 6.
Yeah.
Why not? Why is there not 14 plus 15 in 7?
You mean first add these one. First add these one.
No, you mix at the same time. So when you pass the 7 to 6, in the same time you put.
All at the same time the number.
And then they can. Do
Yeah. Yeah. So in the same transfer. Yeah. It doesn't fit our model, but you could do it, right? Because we said it takes unit steps, right? But a similar thing, but is why transfer these things one after the other, right? Why not first add them here? Instead of adding them after they've been transferred. You can just add them immediately and then reduce. Right? Now, this might not seem spectacular here, but if you have a lot of numbers, right, you can do a lot of additions without any communication step. Right?
Then you're back again to the sequential.
And then you're back again to the sequential. Well, we see what that means. Right. So what we do now is to do what I said. You first reduce on the processors and then do the summation. right? A reduction summation. What we have here is that locally the calculation time is n over p, right? And that the global is log p, because each processor only has a single number left, right? So the total execution time is n over p plus log p. Now the question is that fast optimal? Difficult to say, right? Because we have two variables, right? N over p, and we have to get rid of one of them, because otherwise we never end up with 0. Sorry, with 1. Well, if we write the cost here, this is n plus p log p, because if you multiply the parallel execution time, then this term becomes n, and this term becomes p log p, right? And if we assume that n is lower bounded by p log p, right, we can replace this term by n. So n must be larger than p log p. And then the cost is order n, and our sequential time is also order n. Ergo is cost optimal, right? So you see that by clever manipulation you can still derive in terms of scalability a cost optimal solution. And this is a trick which you often do, right, to get rid of one of the variables, to assume a relation holds between the two variables in order sense. So that n is lower bounded by p log p, and you replace it here by n plus n is 2n, but it's still order n. It's all asymptotic analysis, right? I mean, you're getting rid of all the constants, which in practical cases matter, by the way, but for the scalability analysis, it doesn't. And since we're talking a little bit about the efficiency in terms where we can still derive a cost optimal execution. Right. Now, I didn't have a lower WT representation of this algorithm. We now talking about a scheduled algorithm, right? Because we allocate P processors to a more limited amount of input numbers. Well, here is the equivalent of our optimal program. It looks somewhat more complicated than the other one, but if you look at the details, it's not. It's still, it's now 4 steps, right, with a number of sequential and parallel loops in between, which basically realize the operation I've just shown. Each of these steps, again, can be turned into an expression, right? This is step 1. This is step 2, this is step 3, and this is step 4. And if so the parallel execution time, the workload is expressed like this, and the parallel execution time is expressed like this, right? Because this is done then again in n over p steps plus log p plus 1. This is the final step here, and we see that it is n over p plus log p, which is the same complexity we have derived by the graphical example. So it's nice to see that from such a, at first sight, very complicated program, right? Because if we wouldn't have known this, and we only would have been given the program, you can still derive this expression. and do some order analysis on the program you have. Right, same. The only difference with the previous slide is the extra copy steps at the start and the end. Right? Okay. Something about scaling. We have that the efficiency is equal to S over P, which is equal to sequential execution time divided by the parallel execution time times the number of processes. Right? If we rewrite this expression by substituting P times the parallel execution time by the overhead plus the sequential execution time and do some algebraic manipulation, we get this formula. That the efficiency is equal to 1 over 1 plus the T overhead times the sequential execution time. Let us go a step further and take again the example of adding n numbers on P processor in an optimal way and assume that each addition step and each communication step take unit time. So whether we do a communication step or an addition step, it still takes unit time. Then the parallel execution time is equal to n over p plus 2 times log p, because in the reduction here the things are local, right? So we only have the operation times, and here we have to do a communication step and an addition, which is 2, right? And that log p times, and we're done. Yeah? This is of course not realistic because the ratios are usually somewhat different, but for the example, this holds. Then the speed up is just n over n plus p plus 2 log p. Actually it's n minus 1, but for the sake of convenience and easy formulas, I have just substituted n instead of n minus 1. Because it's a sequential execution time, right? It's n minus 1 steps. So the efficiency in this definition, if we divide this one by p, is equal to 1 over 1 plus 2 p log p divided by n. Just simple filling in the formulas. Now let us see what happens if we make a graph of this efficiency, filling in various numbers for p and n. So we have graphs here showing n. N starts here, the deep blue line is 64, and the light blue line is n is 512. This is p is 1, this is p is 4, this is p is 8, and this is p is 16, and these are the execution times. Now you see that for this one, the efficiency drops faster than for this one. But there is a peculiarity in this graph and these numbers. Can anyone see that? Because this is the efficiency, right? Sorry, this is the efficiency, these numbers. There's something which is a bit peculiar. Yeah?
Different numbers of numbers, so to speak, can result in the same efficiency.
Exactly. Different combinations of P and N yield the same efficiency. These ones. So the combination N is 64 and P is 4 is efficiency of 80%. The same holds for N is 192 and P is 8. And the same one holds for 512 and P is 16. Right? That means that if we pick the right combination of the pairs P and N, we can still obtain a constant efficiency. And constant efficiency was connected to optimality. Right? So the conclusion from this example is that the system can remain cost optimal, meaning an efficiency of order 1, right, if N is equal to 8P times log P. Right? So if our number of processes grow, so does N has to grow in order to obtain the same efficiency. Right? Okay, let's leave it for this hour and continue the next.